So, I was asked to speak on fundamental physics. I added with gravitational lensing. I thought about with and instead of. That's what I settled on. So I'll do my best. I'm mostly going to talk about modified gravity and tests of gravity. It's a very active field, so I apologize for the lack of any attempt at fair referencing, but I'll mostly borrow from things presented in these two papers and the Komatsu et al. WMAP paper. So I'll talk about the state of our universe in terms of its fundamental parameters, some dark energy, and then the bulk of the talk will be modified gravity, how to test for modified gravity, what role lensing plays, and how to combine it with other probes. So this is a brief summary of the parameters of our universe. The initial conditions appear to be remarkably similar to what you'd expect from an inflation-like scenario for the early universe, which is to say Gaussian initial conditions, nearly scale invariant power spectrum, spatially flat geometry, which is not to say that inflation is the correct theory of the early universe. There's a lot of work on string-inspired or high-dimensional or collapsing scenarios that might produce similar initial conditions that I won't talk about. Cold dark matter, as you all know, and then there's this bit about the fact that the universe is accelerating at late times, and if we ask the question, why is it accelerating, you get into a lot of trouble. So that's what I'll mostly talk about. As you probably know, the three scenarios for explaining an accelerating universe currently are lambda, vacuum energy, where pressure is minus the energy density, or some generalization of it, where there's some vacuum-like energy density called dark energy, which has some dynamics, and an equation of state parameterized by W, which is pretty close to -1, the data tells. The third scenario is that we don't need any dark energy. We can get an accelerated universe if general relativity breaks down in the right regime so that the Friedmann equation is no longer true, and then you can get an accelerating solution with just matter. So let's look in a little bit more detail at WMAP and its friends, namely the supernovae, BAOs, and other probes of the low redshift universe have told us about the fundamental parameters. We know the power spectrum isn't exactly scale invariant. It has a red tilt. The tensor scalar ratio is consistent with 0. The upper bound is 0.24. Neutrinos, we know from other means, are massive, but cosmology tells us the sum of the masses is less than half an eV. And there's been a lot of interest in probing primordial non-Gaussianity, which is related to various scenarios of inflation and other theories. And the constraints on the parameter FNL, which describes a certain kind of non-Gaussianity, have improved to it being between -5 and 59 at 95% confidence. Sigma 8 isn't sort of direct fundamental parameter probed by the CMB, but it's constrained pretty tightly when you combine the CMB with the H0 measurements and the BAO. So by the way, in this WMAP analysis, they use H0 from either the strong lensing work that Sherry Sui presented yesterday, or just a small subset of very low redshift supernovae. So the Hubble Key project and constraints from the full high redshift supernovae have been dropped as representing the state of the art. So sigma 8 is measured to be 0.8 with 4 or 5% error bars. Sorry, 3 for dark energy parameters, they, for some reason, switch to 68% confidence levels. I guess the error bars don't look so good if you stick to 95%. And then I haven't shown the constant W measurements because, in my view, if you're going to allow W to be free, you really need to allow it to evolve as well. So you have to use at least this 2-parameter description of dark energy, and you can see it's consistent with -1. We know very little about its possible evolution. And even to get this information, they held spatial curvature to be 0. So if you allow curvature to float, the WMAP team doesn't give you any constraints in W0, W8. They do give you a constant. So that's what we know about, sort of roughly speaking, the primordial universe and the expansion of the present-day universe. So the universe is simple, extremely simple in many ways, except for the small departure from scalar variance that you do expect from inflation. And it's unsurprising, barring for this minor issue of W being -1, whereas everything we know from the universe gives a W close to 0, or plus a fifth radiation. So, so what questions remain for low redshift observations? I mean, WMAP and the CMB have been extraordinarily powerful probe. The accuracy of the measurements and the richness of features in the power spectrum have allowed us to learn about many different physical parameters from it. So what can we still learn from low redshift observations? Which is to say, why the fuss about dark energy? So dark energy, as you know, becomes important only at redshifts below 1. Hence the need for low-Z probes to learn about dark energy. I mean, there are scenarios of dark energy where its density is non-negligible at a much higher redshift, but it's certainly a significant player only at Z below 1. So the puzzle about dark energy, aside from the fact that we have an energy component with a strange equation of state like that to begin with, aside from that, the puzzles are that its energy density is very small, 120 orders of magnitude smaller than you'd normally expect, but it's non-zero. And of all the small values it could have had, its omega dark energy equals omega matter. So this is the only place in the stock where I'll use the equality sign as used by string theorists, which is to say it's equal to omega matter times 2 or 10 or 1,000, you know, any number for which there's a word, like a billion. But it's not 120 orders or 60 orders of magnitude at all. And so that is genuinely a coincidence problem. So these are pretty extraordinary puzzles. They connect fundamental physics and cosmology. And we, as far as worthwhile ideas goes, we have an empty set. So the action is with data, in particular low redshift data. We're groping in the dark and we really need some more empirical input to get clues. So let me show you just a couple of samples of the low redshift universe. This is a compilation from Tegmark and Zeldariaga, recently updated, of what happens if you put all observations of clustering in the universe at all redshifts. If you put them together by scaling with the linear growth factor for lambda CDM, then you get this apparently beautiful agreement. I say apparently beautiful because it is impressive, but there's a lot of orders of magnitude on the y-axis, so one should bear the error bars in mind. And to give you a flavor for what other fundamental physics one can still learn from the low-Z power spectrum, there are plots of a modified inflation scenario that has a stronger tilt and a significant component of dark matter in something that's not cold, that would change the power spectrum at high wave numbers. So the CMB has been translated from redshift 0, from redshift 1100 to redshift 0, and so you can see that to this degree of approximation, the structure in the universe really has evolved according to our understanding of linear perturbations and lattice theory. You can also see that there's some significant overlap in scales between the CMB and galaxy clustering, so that's a persuasive check of the shape of the power spectrum and so on.